Pleased to be speaking to you today about AI applications in cancer care, an overview of opportunities and challenges. I'd like to start off by acknowledging my disclosures and the funders I've had for the last few years who've supported some of the work you're going to see today. I'm a head neck radiation oncologist with the largest U.S. radiation oncology head neck team at MD Anderson Cancer Center, where we see over 1,000 head neck cancer patients a year. We're part of a larger multidisciplinary team that treats head neck cancers with a focus on reducing side effects and maintaining excellence in oncologic care. But my research area focuses on complex computational approaches for symptoms and minimizing the side effects of radiation therapy for patients who have head neck cancer. I also work with a series of computational scientists on big data applications and on operations research applications for decision support in radiation oncology. And these awards fund much of the information that you're going to see in some of the examples. I'm also fortunate enough to have an exceptionally talented lab team you can see here who provide much of the content expertise and multiple alumni who've contributed over the years. Finally, I think it's important that all of us as oncologists are thankful for our families and the families of our patients, because our goal is really to return our patients to those who they care about. In radiation oncology, my specialty, the future certainly will include artificial intelligence. Radiation oncology has a long history of deploying novel technology for patients, and AI is going to be a part of the future. Importantly, though, it's unclear the path that it will take for us to get from this disruptive innovation in technology. But I think all oncologists generally, and radiation oncologists specifically, should have some familiarization with what is artificial intelligence, what are the considerations with informatics and big data. And so the point of this talk is going to be to outline some of the roadmaps, obstacles, and operational considerations specifically for radiation oncologists, but for oncologists generally. Before we get started, I'd like to talk about a few definitions. First, you're going to hear me use the term informatics. Informatics is the discipline of data implementation, processing, and storage. Information science is a broader field. I'm a clinical informaticist, and so the people who perform or utilize these operational approaches are often informaticists. Artificial intelligence is a research domain within informatics. It's focused on computer systems that can perform tasks that normally require some semblance of human intellect, such as visual perception, speech recognition, decision-making, or translation between languages. Big data defines the inputs that are used by artificial intelligence. Big data is information that is either large in volume, has lots of iterations, or has a high amount of variety. Essentially, more data than a human can reasonably incorporate within an insight or decision-making process. The methodology by which artificial intelligence falls into a broader category called statistical learning or machine learning. And these are algorithmic computational approaches that can make predictions on data given some prior estimator. So the sentence that you'll see at the bottom, informatics lecturer at the AI conference gave a talk on what machine learning approaches to use for big data, makes total sense. Now, again, when we think about artificial intelligence as a broad field, it's any computer program that can learn through some kind of iterative input function. Machine learning represents the specific algorithms whose performance can improve as they have more repetitions of these iterative data inputs. And finally, deep learning is a subtype of machine learning that uses multi-layer neural networks. Now, a lot of folks will use these terms interchangeably, or they'll call something AI or machine learning, but there's some discrimination here in terms of breadth, scope, and the era in which they were developed. Big data is a very broad term, and it's unclear a lot of times when people use the term big data exactly what they're talking about. From his book, Predictably Irrational, famous scientist Don Ariely says, big data is like teenage sex. Everybody talks about, nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they're doing it too, and most don't do it very well. But in a sense, big data is something that's quite important because it represents the multiple streams of information that we as oncologists have to deal with. Everything from the individual patient's health record and what's going on with that case to clinical information about from the EHR, imaging data, or treatment data such as radiation dose. At the population level, this is aggregated, retrieved, but then can potentially be used for knowledge generation which could then be back applied to the patient through personalized risk assessment. There are multiple types of machine learning, and I won't belabor these other than to say that there are some types that require some idea of the data structure, and there's others where we can highly supervise the process. So it's quite rare to find someone who is in fact particularly good at all different kinds of machine learning. Most of us pick some kind of flavor and develop expertise in that. It's also important to realize that the relative benefit of big data or machine learning applications scales as a function of the cost of data acquisition. So for example, there are large population health registry data sets. These in the United States are things like SEER or Medicare or NCDB. What's important to realize about these applications is these large-scale population data sets often have very low granularity. They're very cheaply collected, but they don't have a lot of information about an individual patient. On the other hand, there are these very, very rich, very small data sets which are often housed inside academic medical centers. But the problem is they're so tiny and they're so deep that we don't really have access to them. So where the biggest gain happens is in this interstitial period where there's the capacity to move from population level information all the way down to this highly granular, high-cost data. That said, most applications of big data are opportunistic. So people are using the data they have access to rather than the data that is to answer specific questions. And so what you're seeing in biomedical science right now is just like in this cartoon, people are just aggregating the data that's available at their particular facility, which tends to be this kind of borderline between quality reporting and population level reporting, or at this interface between research and decision support, right? So not really operating at full scale. Because of this, it's important to realize that the fields that implement this require a multidisciplinary team. So there's an entire field of biomedical informatics that incorporates computer science, engineering, biological sciences, statistical and decision support, cognitive and social considerations to help facilitate this. And in fact, for radiation oncologists, there's a special place in our hearts for biomedical informaticists because Ira Kalett, who wrote the book that many of us used as a textbook before he passed in 2015, was in a radiation oncology department at the University of Washington. And so there's been a tight alignment with the radiation oncology community and the biomedical informatics community since at least the early 70s. This is reflected in a special article that came out a few years ago in the International Journal of Radiation Oncology, Biology, and Physics that talked about this need for technology innovation in radiation oncology. And this holds true for artificial intelligence as well. In that there is still, in order to achieve this, a need for integrating databases across the discipline. So taking data from individual data sets housed in individual academic centers and aggregating them. Tools to help discuss these treatment options, that is making the algorithmic components overt, informatics domain expertise among oncologists, which to be fair right now is highly lacking, and then these tools to deliver the algorithmic or AI resources at the point of delivery. Now, because of this, though, if you look at how well people are doing with this, I can tell you that health informatics with machine learning is honestly in its infancy. The majority of hospitals have electronic medical health records in the United States, but very few systems employ them at scale. Stephanie Combs and Kirsten Kessel from the Technical University of Munich did a survey fairly recently where they looked at 895 articles about electronic data collection at health systems. And so in the end, there were 268 which were valuable for interpretation. But if you look at the number that were actually implementing these large-scale clinical analytic tools, right, using the electronic health record for analysis as opposed to just patient care, they're only able to hold 5. Now, the number has increased a little bit since then, but I can tell you broadly, most of us are using the EHR as a treatment tool, but very little of us have access to it as an information source. The major problem that Kessel and Combs found was it was not the lack of technology or tools, but the lack of expertise, specifications, and concepts. And most key among those was the lack of standardization. So that when there was a need for a tool, most researchers completed some in-house one-off solution without using existing informatics standards. So the end users would come up with some little workaround that only worked in their home environment, but did not fit further application. This points to a huge unmet need in AI, which is the need for data standards. Data standards are non-trivial to develop. You have to identify the data elements for a decision criteria, create a database of how that data is represented, standardize that across institutions, make a public data set, and then continuously review it. But if you don't do that, communication across health systems and the aggregation of the data needed for AI development is exceptionally limited. This lack of a common ontology or lexical system, i.e. a common terminology set, is what is so ubiquitous that there's a cartoon from the 80s in the Far Side that calls this the ginger problem. So the idea is, here is the man saying to the dog this complex semantic information. Okay, Ginger, I've had it. Stay out of the garbage. Stay out of the garbage or else. And the only content that gets across is that the dog is aware that it's being addressed. Without a common terminology, all the content is obscured. And so you may be sending huge amounts of information into a system, but the relative information yield is low. Developing these standards and ontologies is critical and occurs across voluntary bodies. ASCO and MITRE are undertaking this right now, but functionally speaking, this is a key consideration. For radiation oncology, we did this recently, where we just started to try and name organs at risk across different institutions. So for example, we went to physicians, physicists, vendors, and we put together a group to say, how can we just name objects the same name if we're treating it? So for example, if you were treating organs at risk with radiation therapy, you might see something called the cerebellum at one place, but it might be called cereb at another. You might see a brainstem called brainstem written out like this. You might see it written like BS. So this just now showed that we were agreeing on those ontology names. Here's another good example. In radiation oncology, we often code things as local recurrence or a regional recurrence. And that comes from an era when all radiation fields got the same dose. If the tumor came back within the radiation field, you could know that it received the full dose of radiation. But now, with techniques like intensity modulated radiotherapy, it's common that you might have a recurrence in one region that received very high dose, but you might also have a recurrence in an area that received a lower dose. To treat those as if they were the same type of failure is incorrect. So a few years ago, we came up with an ontology to classify the types of failures relative to the radiation dose. And by doing so, this allows us to communicate across institutions what the actual outcomes are. The problem with standards is that everybody ends up coming up with their own standard as well. So this XKCD cartoon illustrates exceptionally well. The initial situation is that there are 14 competing standards. And so everybody says, this is ridiculous. We need one standard that communicates and covers everyone's cases. And in the end, there's 15 standards, none of which is used ubiquitously. So this lack of standardization is, I would argue, an exceptionally core barrier or challenge to AI development. The other big difficulty with AI development is it's difficult to understand what people did when they developed one. So recently, Luo et al. Generated a guideline for how we should report machine learning predicted models, because we were getting tons and tons of publications where we couldn't effectively understand what was done. So like a consort diagram for machine learning papers, this provided a guideline so that you could at least tell if people were taking reasonable and necessary steps. So you could tell whether people were preparing the data for model building, what were the types of inclusion criteria, the time span of the data, validation metrics, how the prediction model was built, what kinds of modeling techniques were used. You can see that machine learning and AI is a non-trivial task, but it's almost as hard to express to people the reporting structure in an effective way in the context of current publications. So when you look at these include things like it's important to realize that a lot of times an AI algorithm doesn't have a publication that states how this could be clinically used or the limitations. And so if you were to go and just use an AI model because you read about it in some article or you bought it from a vendor, it's unclear if they had lots of unexpected results and really had to tune the model. So these things are important to kind of understand. These baby steps are important because we have to understand that the clinical implementation of AI is quite hard. And this is due to the nature of big data, the sparseness of it, but also quality assurance. And we'll talk again why the nature of machine learning and AI algorithms is also different than classic statistical techniques. It's very difficult. You probably won't see many randomized trials to test AI algorithms. Part of this is just the nature of the data. So low dimensional data is that can be held by a human in their head. So it's a local data dictionary, which is what your brain is. It has relatively small amounts of complexity. But when you think about the information that's contained in things like literature, this is where we're used to sharing aggregated data. Tables that have multiple values that are too big to remember would be in this category. On the other hand, when you think about triple stores, logic maps, or semantically annotated high-dimensional data, you really can't keep this kind of information in your head way over here. But it's also hard to represent in things like two-dimensional tables. So the knowledge representation gets really hard. It's also important to realize that different kinds of machine learnings can give you different kinds of outputs. And if you push to fit the model to your particular style of machine learning or AI, you'll often get out what you put into it. So for example, if you take this data set, which is the same data set in every frame, and you say, I'm going to use a linear model, well, you'll get a linear model. And if you use an AI algorithm that looks to fit a quadratic, you'll get a quadratic. If you use logarithmic, Loess, etc. So in the end, it's just like curve fitting in the sense that if you come in with a prior approach, you will often be able to generate an output function of the data that matches your initial parameters. It's also important to realize, though, that this idea of moving is also culturally limited. So a lot of people hold on to data because we grew up in an era where we were data poor. So if you had a bunch of patient data, you would hold on to it and publish it for yourself rather than sharing it. And computational power was limited, so you could only do simplistic analyses. What's changing is now we are living in a world that's increasingly data rich. It's quite easy to store and transfer gigabytes of information, which was not the case even a few years ago. And near limitless computational power now exists. And so because of that, this transition from a culture of data hoarding to data sharing really benefits. Because of that, we can now try all these fun techniques on our big data. So here's a good example. Let's imagine that you're trying to correlate overall survival and total dose of some structure. Well, historically, you would just draw like a single simplistic line, but now you can use these complex approaches to find thresholds or breaks within the data using things like support vector machines. So again, here's total dose, and you can say, I want to discriminate total dose and the size of the gross tumor volume. You can see here's a split. Well, this allows us to then make these demarcations as individual thresholds. For things like modeling tumor control, you can use more complex approaches, and then you can model those against classic approaches. So the support vector machine approach, which you see here, gives you something that works about as well as the other types of approaches that you could use using standard models. One of the key features that people bump into is that these machine learning algorithms comes in tons of different flavors. So the simplest are these things that are widely used in radiation oncology called decision trees. And then the more complex are these artificial neural networks. Each approach has their own advantages and limitations. So if you were to just pick one approach and try it, almost all of them will work, but they have various considerations in terms of their advantages, their limitations, and when they're most effectively used. So it becomes incredibly important to identify which approach is fitted for the data you have and the clinical problem you have. Here's an example of that. The different types of machine learning approaches have different degrees of flexibility, the kinds of problems that they solve well, and how interpretable they are by humans. So neural networks have very low interpretability. It's very hard to explain how the algorithm got to where it was finding the solution. Whereas things like lasso regression are basically just like a penalized multivariate regression. They're very simple to understand. However, these work in a much smaller subset of cases than neural networks. So finding a good balance between these is pretty important. So I'll use an example just for illustration from the creator of generalized additive model trees. These were developed by Leo Breiman in starting in the 50s all the way through 2001. Now, Breiman was pretty bright, and one of the things that he led to is a famous paper called Statistical Modeling of the Two Cultures, which everyone should read like immediately. Breiman talks about the fact that there's two cultures. The traditional statistical modeling culture assumes that the data is generated by a random process and that you can fit it to something like a normal model. And this is, in Breiman's mind, led to irrelevant theory, questionable conclusions, and kept statisticians from working on current problems. The machine learning or algorithmic culture uses algorithmic data, treating the data mechanism as unknown. So machine learning approaches broadly don't care much about the structure of the data. They presume that they will model or learn that through iteration, as opposed to statistical theory, which assumes a prior function in order to overcome the sparseness of the data. So Breiman says if our goal is to solve problems, you have to move away from dependence on data models and support more tools. These tools developed by Breiman et al. Were first implemented in oncology by a series of publications by Laurie Gaspar, where they took randomized controlled data of dose information for patients with brain metastases on a series of trials from the 70s and 80s. And they looked at various radiation doses and fractionation schedules from 3 trials, and they grouped the patients and said, okay, let's use this tree-based approach to determine iterative risk categories. So they said, okay, if you've got low performance status, those patients do quite poorly. All right, if you've got this intermediary risk grouping, but if all you've got is brain metastases and you're young and your primary is controlled and your performance status is good, well, then you're in a good risk category. So this is a very simplistic but very effective machine learning technique called a recursive tree. We call them RPA, or recursive partitioning analysis, in radiation oncology. Everyone else in the world calls it classification and regression trees. But then this gave us this risk groupings, which have been used for many years since. So because of that, radiation oncologists love RPA, but we've really never thought of it as machine learning or artificial intelligence, but that really was what it was, this early step in that process. Let me give you another example, though, of how these RPA type approaches are used. We did a study a few years ago where we looked at dose response information for muscles in the head and neck. So all of these muscles in the head and neck get some radiation, and that radiation leads to a risk of injury. Here it's swallowing. Patients with swallowing dysfunction have dose volume histograms that are much increased for the digastric muscle or the intrinsic muscles of the tongue, or in pharyngeal constrictors. But you can see that the shapes are quite different for all of those different muscle groups. So we used the same RPA-based method you saw before to find individual thresholds where there was the highest break between some dose level and some volume of dose to the muscle to predict high risk of swallowing dysfunction. And that allowed us to then use that model to say, well, it seems that if you're trying to predict who's going to have problems swallowing after radiation, it's the volume of the mylohyoid muscle over 69 gray and age, the 2 best predictive functions. So we were quite pleased with this in our oropharynx patient data set. Well, the problem was using a different technique, a lasso penalized regression. Some friends of ours had shown in another head and neck data set that the pharyngeal constrictor muscle and the cricopharyngeus muscle were the best predictors. How could this be the case? How could we have found a totally different organ at risk was the causative site of post-radiation dysphagia to our friends and quite impressive and brilliant colleagues over at University Medical Center Groningen? Well, the answer was we were both right. We had used different data sets. We had an oropharynx data set that had high dose to the mylohyoid. They had a primarily larynx cancer data set that had dose to the cricopharyngeus. The dose variation in the models and the outputs of the models were due to the input data, not some intrinsic property of the dose. And this points out a key pitfall of machine learning or AI algorithms, is that the results you get are not necessarily generalizable to data sets that don't look like the data set that you were trained on. This is something I think is an important thing to realize, because in all of the progressions that you've seen recently, there's been tremendous improvements in AI applications, but the clinical data sets and the questions underlying them are going to have to be considered as well. So if you look at, from the Leo Breiman era, which was here in the 70s, these early considerations in the 1940s of the idea of AI, from the 70s to the 80s, there was this period which was called the AI winter. This area is when there was not sufficient data or computational expertise to really move the ball forward. But then deep neural networks started taking off, and what's been called the second AI golden age started in 2010. Geoffrey Hinton is famous for this, as from the University of Toronto, as one of the researchers who started this. And he kicked a lot of radiologists and radiation oncologists into high gear when he said, I think if you work as a radiologist, you're like Wile E. Coyote in the cartoon. You're already over the cliff, but you haven't looked down. People should stop training radiologists now. It's completely obvious in 5 years, deep learning is going to do better than radiology. Well, he's only got 1 year left, but I can tell you that the fear that AI will replace my job dropped off a cliff the first time I tried a deep learning model. In fact, it's very unlikely that this will be the case, and I'll explain why, even though this is a phenomenal tool. So those historical AI models from the 1950s and 60s used a technique called a perceptron, or an early neural network. And so what they did was, you had a series of input units, like let's say pixels of an image, and then you hand-coded the features, and then you performed adaptive weighting to determine how much each individual input function could predict the output classifier. So it's a neat learning algorithm for adjusting the weight of some kind of model. The second generation of neural networks added something called a hidden layer. And this is essentially a backpropagation of error signal to get derivatives to increase the learning accuracy. So that so instead of just a direct input to output matching through a single layer, the hidden layers allow iterative weighting and feature selection simultaneously. So this was a great improvement. This perceptron that is usually used to classify the data into two parts. So a binary classifier. And what occurs then is these inputs are in place, but the weightings can vary, and then the weighted sum of these weights then can put an outputter of the step function. By using this information, you can approximate all kinds of linear and semi-linear and nonlinear activation functions. So the shape or the structure of the data does not really matter as much as it would in a classic regression, where you have to know what the output function does, or model that sufficiently. So the idea of these hidden layers means that the neural network is able to, that has multiple layers, and deep neural networks have many, many layers. It iterates this process, and through iterative improvement has greater performance estimation with more features. In 1998, Jan LeCun came up with LeNet, where you could take each of these subcomponents of a pixel, you could perform a convolution with subsampling, and perform this over and over through multiple loops in what it was kind of an early implementation of modern deep learning. This convolutional neural network in 1998 goes back nearly, now more than 20 years, but it really booms around 2010. So if it existed, why weren't we seeing these convolutional neural networks back in 2000, let's say? The real reason was there wasn't enough data. These classification methods need huge amounts of data to train effectively. So when you had massive amounts of let's say, internet pictures of cats, well, then you could move to things like cat localization and detection, or image segmentation, or even these kinds of transfer like approaches, but it took huge amounts of data to get there. This is because once the availability of the data became available, you could now start to put in huge amounts of learning sets and take this information from the convolutional network. Now, what's nice though is that convolutional neural network, each layer is learning different things. You can detect things like edges, texture, parts, subclassifications, and so these are very robust against a lot of types of learning problems. But again, the problem is while each layer learns different information, the total output is very, very difficult to express in a condensed form. So you kind of have to just trust what the neural network output is. Because of this, it becomes important to not get carried away in the hype cycle of AI. So almost any new technology has this new trigger. It becomes new. There's a period of inflated expectations. AI will solve everything. Then everybody says, oh, AI is awful. And those of us who remember the AI winter of the 80s and early 90s remember when this was the case before the slope of enlightenment and the plateau of productivity. On the Gartner scale, it appears that machine learning, and I would say AI, is kind of about to hit this disappointment phase. And I, whether you agree with that or not, it's important to realize that machine learning will solve a huge amount of things, but it takes an extra amount of work. Let me give you a good example of the kinds of pitfalls we have to avoid. So we did a machine learning radiomics challenge a few years ago for the Mackay conference. As many of you know, there's about 20,000 U.S. cases a year of oropharyngeal cancer, which is epidemic due to HPV infection. There's now more HPV-associated head and neck cancers than cervical cancers. And these cancers are virally associated with the human papillomavirus. Those patients then have a tendency to develop a higher risk of head and neck cancer. However, those head and neck cancers are markedly more curable with radiotherapy and chemotherapy. So you can see that the HPV positive patients have a markedly greater survival compared to HPV negative. So it's an etiologic agent that predicts outcome. So we ran a challenge where we said, okay, we're going to perform radiomics analysis. Radiomics takes images, does a pre-processing, and converts these image features into individual numeric data across many, many types of different analyses. So it converts this one image area into thousands of potential image variables. Those can then be used for feature extraction and used to validate information as a prediction model. There's lots of data suggesting that these radiomics approaches can be used for classification of head and neck cancers for things like HPV status or tumor grade, normal versus abnormal. But all of them are fairly small data sets, just very pilot, very tiny, and probably insufficiently powered to really say much substantively. The largest of these data sets is a mixed data set of head and neck and lung, and you can look at things like individual survival, and there may have some value as well in these bigger data sets. So we ran two challenges to see if you can see if image features in the local region predict whether the local oncologic outcome would be tumor control or recurrence. So just local features, do they predict local outcome? And we asked, could you identify just on the images whether this was an HPV positive or HPV negative tumor? That is to say, could you use radiomics to classify HPV status? And we wanted to see if we could crowdsource this innovation by drawing on non-radiation oncologist or non-radiologist knowledge and have a little fun. So in 2016, we did the oropharynx Mackay challenge, and to determine these two challenges, determine from CT data whether a tumor will be controlled by definitive radiotherapy, and predict from CT data the HPV phenotype by P16 or HPV positive. So we gave all of the participants in the challenge DICOM files where we had outlined the tumor and the lymph nodes, and then demographic and clinical data. They were then allowed to use a training set to train their AI model on the image features, and they could check on a public leaderboard whether these training sets had been accurately classified. A hidden test set was available at the end, and so we tested how well they performed on the hidden test set with a private leaderboard. So they could test on this public leaderboard and see if they were getting better, but we would eventually award the trophy and make the announcement at the Mackay meeting based on the private leaderboard. The rules of the game were they were very binary classification. It was only HPV status, yes, no, or tumor control, yes, no. You could use the demographic data, so you had the same information that a clinician would have, and half of the database was in the public and half was in the private data set, but the winner was declared on the private data set. We put in a series of 376 patients in the data set, with 315 that had contrast available scans. We performed segmentation on the tumors in a standardized way, and the prize, we got a free publication in CTRO, a radiation oncology journal, as well as a $7 trophy for the first, second, and third place teams, which I paid for out of pocket. The local control challenge and the HPV challenge both had multiple numbers of teams with lots of players and multiple entries. So we got a lot of enthusiasm for this challenge across the machine learning community. Now, the winners on the private leaderboard of the HPV classification group was a group of 6 biostatisticians from MD Anderson Cancer Center. They came up with a 91% accuracy area under the curve score on the final leaderboard. And the winner of the local recurrence challenge with an even higher predictive score was an undergraduate student from Colgate University who likes to compete in AI challenges. So we congratulated our winners. Well, we were the team that performed for the biostatistics team that performed the HPV challenge. They used a large, expensive process. They used multiple machine learning approaches. They incorporated an ensemble-based model. But the winner of the recurrence challenge did something very interesting. When he was asked to speak at the Mackay meeting and talk about his approach, he said he realized that the extra imaging information from the radiomics data made no impact on the prediction model, and so he threw out everything but the clinical variables. And so he won by not using radiomics. His machine learning approach performed better by just using limited clinical characteristics. So it's important to realize that more is not always better. The need for this kind of approach is important because if you don't have multiple people attempting different approaches on the same data, it's hard to know what's actually being done. So this is a great paper by Hugo Ertz, where they took a series of different classification methods for learning radiomics biomarkers, and they compared those classification methods with different feature selection methods. So these are 2 common components of machine learning approaches. And you can see how you make these classification methods and how you do these feature selections gives you vastly different results. So it's not like there's one right answer. There's kind of the answer you get. And if you don't calibrate that, it's very hard to know. This also points to a huge unmet need in AI for the need for shared models approaches. Anytime that someone does AI-based approaches, if they don't have their software on GitHub or their data available in a public repository like Figshare, the Cancer Imaging Archive, please request that they do so. Hidden information is of little utility in AI. What's really changed the game recently has been the last 5 years, Nature Scientific Data will publish your data or software on PubMed. So this is the data from that radiomics challenge we ran. So not only can people see the data, they can use it to build their own models for further testing. This fits with a larger aim in the AI community, which is called being fair. FAIR is a principle that is designed by Force 11. Force 11 was a Future of Research Communications group. And NIH has endorsed that all data should be machine readable and has to be, so it's not just something that a human can read on a PDF, but something that can be put into a machine and reused later. So data should be findable, acceptable, interoperable, and reusable. The FAIR principles mean that if you use data and perform AI research, you should make that data findable, give it a unique persistent identifier, make it accessible to the community using a standardized protocol, have that be interoperable so people can download that data and use it, and allow people to reuse it multiple times. So this is something that's really critical for the future of AI as we move forward. So we have some work to do. We need better data aggregation, more transparent modeling, stored data sets, and in short, more fairness. All of these are going to make for a rich future. So where will we see AI in oncology first? I think the first place that we're going to see it is in what are, to be honest, fairly simplistic prediction models, where people will take a series of input patient data of various degrees of quality, put it into a survival analysis model, and then generate some outcome. And that may have some utility, but essentially this is no different than staging systems or nomograms, just performed in a more effective manner. The second area I think you'll see implementation coming fairly soon is in segmentation tasks. So it turns out that humans are really bad at segmenting things. It's really difficult for radiation oncologists to say, okay, this is the gross tumor volume, this is the node. But it's even harder when you ask radiation oncologists to identify what areas should be treated for microscopic disease. And if you give the same head and neck radiation scan to 9 radiation oncologists, you'll get 9 different segmentations that can vary substantially. So one of the major advantages to using machine learning approaches is they can take a series of prior data and create a new segmentation that's quite reproducible considering the prior. So for example, this is a DICE similarity auto delineation project by Carlos Cardenas, where we fed multiple different inputs into a machine learning model. And so if it creates an automated target delineation based on an imaging input. Now, the issue is this works very well at MD Anderson, but it was trained on MD Anderson data. So if you use this model, you'll get segmentations that look like the data that we use. And if you do use data that's from a different source, your data would look different as well. But it's a nice tool for automation. This is moving in a better direction as you get more data. So there is a process where if you have multiple different input features, different kinds of images, you can then do a complex series of automatic segmentation and pre-processing. But the different kinds of MRI data give you different information. So when this kind of information is included, you can actually get performance that does better than a human, because it's able to incorporate more different kinds of images for segmentation than a human can incorporate. And I honestly believe this is the future of image segmentation, is that because humans are so bad at it and multiparametric imaging provides such rich data, that someday we'll actually have machines doing the image detection. We're already seeing these image detection tasks outperform radiologists at things like evaluating whether there's extracapsular extension. So this is a publication by Sanjay Neha and Ben Khan, where they could take radiologic images and determine with great accuracy whether there was going to be extracapsular spread and therefore a need for chemoradiation therapy in patients with head and neck cancer. So these illustrations show us where we are right now and what the kind of initial first steps are for artificial intelligence. And there's a wonderful paper by Robert Challen that I encourage everyone to read, because here's where we are right about now in terms of considering the amount of automation, which is low, and the types of efforts that AI is solving at the moment. Right now, it's things like risk calculators, simple risk scoring, or prescribing decision support. Should you give this drug with this other drug that has an interaction? Yes, no, very basic things. But in the short term, it's moving to these diagnostic support and multifactorial risk model or tailored radiotherapy like the examples I just showed you. Eventually, we're going to move to an area where the management is automated for the patient. So things like autonomous ventilation or automated drug, personalized drug protocols, so adaptive chemotherapy regimens, things like that. At the moment, almost all of the AI approaches that are being used clinically in medicine are reactive, rule-based, require manual update, and have limited design behavior. But the long term is really more towards these reward-driven active learning approaches. The important thing for us as clinicians is that these implementations have to keep patients safe. So Challen et al. Lay out 4 different considerations. So one is distributional shift. Has the system been tested, the AI system been tested in diverse locations? Does it scale so that it doesn't contain bias? In the United States, ethnic bias is huge, so if you have a system that's trained on only white patients, it may not perform as well on Black or Hispanic. Do the labels represent a ground truth outcome, a live dead, or a clinical opinion? Are there imbalances in the training set? Who is going to monitor the system, or how will it be maintained over time for things like prediction drift? The second is, does the system adjust its behavior when there's high impact negative outcomes? So it's fine for machine learning models to have 95% accuracy if the classification error results in calling a picture of a dog a cat. But if it kills a patient because you've got a misclassification, you've got to avoid those errors even if they're numerically rare. So this idea of out of sample or use case or edge case inputs, if you get an inappropriate input, can the system adjust its confidence accordingly? Does the capacity for black box decision making, unsafe failure, and automation complacency have safeguards? Are these prediction systems interpretable? If the physician notices that the system or AI algorithm's prediction looks wrong, is there a way to stop and test that? Is there a confidence estimator of how sure the system is? Is the certainty of prediction communicated to the clinician in a good way? So instead of nudging, so as a nudge as opposed to a rule that the physician feels like they need to follow. And finally, what happens when the data changes? If there's outmoded practice or self-fulfilling prophecies, how does the system accommodate breaking changes to clinical practice? For example, none of the models we've built in our system have any implementation of immunotherapy. Why? Because we don't have any training data of sufficient size to consider it. Immunotherapy is a game changer in clinical oncology, but it's not represented in almost any of the AI practices because it takes large amounts of historic data. This also is important because there are certain aspects of clinical practice that may be biased that are reinforced by AI systems undetectably. So with that, I'll close, but I thank everyone for their time and attention. I think the future of oncology and radiation oncology within that firmly lies within machine enhancement and AI, and I welcome your questions and comments. Thank you very much.